So my name is Schmidt. I'm a researcher at LATMOS in Paris, and I'm going to be talking to you a little bit about a moon of Jupiter called Io. So the visible measurements that I'm making to support these missions mostly come from Apache Point Observatory. This is a 3.5-meter telescope in New Mexico, and it's shown here on the right what the telescope looks like when it's looking at the moon. When the Apollo astronauts visited the moon, they left retroreflectors on the surface. They left mirrors on the surface of the moon. And this green beam of light is a laser that is shining and hitting the moon. It's about a 1 square kilometer surface area that beam covers when it hits the moon. And the mirrors reflect the light back to the telescope, and you can use that information to get a very accurate measurement of how far is the moon away from the Earth. The accuracy is on the order of about 1 centimeter or so. So this is range finding to the moon being done with this telescope. But for the Io plasma torus, the setup looks like the upper left panel that we see here, where the material is trapped in Jupiter's magnetosphere. It's confined by the magnetic field, which is a very powerful force relative to gravity. And it's along a rotational equator where Jupiter has a 10-hour rotation period. It's moving so fast that there's a centrifugal force where it pushes the plasma as far along the magnetic field line away from Jupiter as it can possibly go. That centrifugal equator is about 2/3 of the way between Jupiter's rotational equator that is spinning around and its magnetic equator, which is tilted by 10 degrees. That causes the Io plasma torus to wobble around Jupiter, and it's not quite along the magnetic axis or the rotation axis. It's somewhere in between. That in-between line is the red curve that we see in the upper left diagram, and when we use spectrographs, we have an aperture which is a slit, and we're imaging what that slit of the sky looks like at different wavelengths. So to study the plasma torus, we need to align that spectrograph slit along this red line of the centrifugal equator of Jupiter. And we have all sorts of scattered light problems from Jupiter itself. So we need to put a mask in front of Jupiter, which stops down Jupiter's bright light by about a factor of 1,000 in order to image it in the same field. So that mask extends about 1 Jovian radii past Jupiter to stop down its bright light, and then we can use Jupiter's reflectance as an absolute calibration source and as a pointing reference to find out exactly how far along that axis we are, how far away from Jupiter the emissions that we see are. So once we subtract off the scattered light from Jupiter by taking our spectrograph slit, looking at the plasma torus, and then pivoting off of it, subtracting off the off bands, which is just scattered light from Jupiter, the spectrum looks like this top image here. So we're seeing different emissions from different charge states of oxygen and sulfur and sodium. Sodium isn't actually trapped on the magnetic field, but is neutral. The ionic emissions have this slight tilt, and that's due to their Doppler shift. They're moving 74 kilometers per second, either towards us or away from us when they're at Io's location. The neutral emissions aren't moving nearly as quickly, and so we don't see the tilted emission from their Doppler shift at distance from Jupiter. The overall temperature range that we're looking at in this top diagram is about 2 to 3 electron volts, and that's relatively cold plasma compared to what's measured in the ultraviolet. We see these 8 different emission lines from different charge states. The dotted line here is where Io's orbit is, and we can see big asymmetries between one side of Jupiter and the other. Sometimes the side of Jupiter, which is near Jovian dawn, if we're on Jupiter, it's sunrise. and Jovian dusk are very, very different, a factor of 2, 3, 4 different in total brightness. We can use that emission to determine the relative abundance of different ion species, and we know that it's mostly singly charged things close to Io, and that as the temperature increases when we move farther out into the magnetosphere, the charge state goes up because things are getting ionized to higher and higher charge states by electron impacts. So during 5 hours, we can map out the radial and azimuthal structure of the plasma torus, and that's because all longitudes of Jupiter in its 10-hour rotation will pass through the edge of our field of view where the column density is maximum. You can use that information to determine the surface brightness, and that gives you the overall ion content. You can get the dawn to dusk overall emission ratio, and we can learn a lot about a feature that we call the ribbon. The ribbon is where the total plasma content along a magnetic field line is maximum. That ribbon location teaches us something about electric fields in the Jovian magnetosphere, and we can use the line ratios between different emissions to determine what is the collision rate of electrons, and is that collision mostly due to enhanced plasma density, or is it due to enhanced plasma temperature where there's a higher pressure that is causing more collisional excitations of the ions. In the ultraviolet, there's a very strong brightness asymmetry of the Io plasma torus. It's typically enhanced by at least 30 to 50% on one side of Jupiter than the other. The reason for that was only explained after the fact. The current idea is that there is an electric field which has a standard orientation in local time that points from dawn to dusk. So we first discovered this when Voyager was taking measurements in the ultraviolet. It came from a direction that wasn't along Earth's line of sight, but a little bit to the side by about 35 degrees. And it measured a particular asymmetry between one side of Jupiter and the other. It then got its gravitational assist moving around Jupiter and stared back the other direction, and it saw the same asymmetry. They can use that information to back out what is the direction of this electric field and how does it align in local time in Jupiter's magnetosphere. So why is there an electric field in the first place? There is a force called the V cross B force that gives you an electric field. The V cross B force on Jupiter happens to point from dawn to dusk because there's a bulk flow of plasma convection moving anti-sunward. That's the V. On Jupiter, the magnetic dipole points south, not like it does on the Earth where it points north. And then the cross product of those two vectors, the V cross B, gives a direction of an electric field which points from dawn to dusk. And that shifts the entire plasma torus towards Jupiter's dawn side. That shift is giving a different ratio of collisions in these plasma species between one side of Jupiter and the other. And when we're moving across a magnetic field, we're changing the local magnetic pressure. The pressure is proportional to the magnetic field squared. And as we're getting closer to the planet, we're increasing the plasma pressure by, if you just change the radius a little bit, that B squared term can change the pressure significantly. It's this increased change in pressure closer to the Jovian dusk side, which is making the dusk side of Jupiter a lot brighter in the plasma torus. So in the ultraviolet, they measure this offset of the plasma torus by its brightness. In the visible, we can actually measure its position. We don't have very accurate pointing from spacecrafts about how far away from Jupiter we are, but ground-based telescopes on Earth can achieve a higher spatial resolution. And because we're using Jupiter as a fixed reference point, we can get it down to almost 1/100th of a Jovian radii in pointing and figure out exactly how far away from Jupiter is this ring of plasma orbiting. The separation between one side of Jupiter and the other is a proxy for this electric fields through this parameter epsilon. And epsilon is a ratio of the co-rotational electric field around Jupiter, which is causing the plasma to co-rotate, versus this standard dawn to dusk pointing electric field. That epsilon is then proportional to an electric field strength, and the field strength that we're measuring in the inner magnetosphere is about 4 millivolts per meter. Relative to, say, the fields on Saturn, which points closer to noon, midnight, rather than dawn to dusk, that's about a 10 times stronger magnitude electric field. So it's enough to significantly displace plasma and move plasma in the Jovian magnetosphere in a way that we're just learning about now. Because the magnetic field of Jupiter isn't centered on the planet, because it's offset a little bit, and because it's tilted, there's a wobbling motion of the plasma torus. And we can look at that wobble motion as Jupiter rotates. The amplitude of the wobble motion is much, much stronger on the dusk side than it is on the dawn side. And it's not what is expected. So the black lines on the plot here on the right would trace out how far along a magnetic field line we can get, and that's the expected plasma motion around Jupiter. But the amplitude that's observed is less than what is expected just based on the magnetic geometry. The reason for that's not currently known. This is an active and unsolved mystery about the plasma torus and its motion in the Jovian magnetic field. Is why is its amplitude not following that expectation? And why is its amplitude different between one side and the other at Jovian dawn and at Jovian dusk? So there's a significant asymmetry both in radius and in amplitude of this ring of orbiting plasma. And the error bars in its position significantly exceed any model fit. So that's indicating that not only is there an electric field, but that electric field is changing as a function of time, and it's changing on short time scales. So that electric field is proportional to other things that are happening in the Jovian magnetosphere, and you can use that as a proxy for what is the loss rate of material that is coming from Io, diffusing through the magnetosphere, and bubbling down the magnetotail and overall escaping the system. The Galileo spacecraft has measured this effects directly. When Galileo is in the magnetotail of Jupiter, it measures what we call plasmoids. And a plasmoid is a bubble of plasma material which undergoes magnetic reconnection and escapes from the system down the Jovian magnetotail. The signature for a spacecraft measurement is a dipolarization event where the field becomes more stretched out, and then it becomes more dipolar when it snaps back like a rubber band. That snap back corresponds to the extended magnetic field reconnecting, forming a bubble of plasma, and then that plasma getting ejected down the magnetotail. That bulk velocity is what's causing this electric fields in the inner magnetosphere of Jupiter. And that's what's giving this overall offset that we're observing with the different telescopes. The location of these plasmoid events, which the Galileo spacecraft has observed, isn't exactly anti-sunward. It is mostly in the pre-dawn sector that's given in these green data points. And it's not really understood exactly why it's there. It's probably that the co-rotational plasma has a certain momentum, which is in that direction, and it and it pushes it so that it's not exactly along the Jovian anti-sunward axis, but it's a little bit dawnward because it has momentum in the dawn direction as it's co-rotating. So the bubbles that are coming through the magnetosphere at close to 50 to 100 Jovian radii aren't actually happening in an anti-sunward magnetosphere the way we usually draw it. They're happening in an offset magnetosphere due to this effect, and that's where they're measured. There aren't very many spacecraft measurements of the plasma torus directly in the plasma conditions around Io. It's not a hospitable environment to send a spacecraft. The energetic particles in that region are very damaging to a lot of components on the spacecrafts, and they try and spend minimal time there. And the orbits of the Juno spacecraft, which is looking down at the Jovian aurora from a close range, are very carefully planned to spend minimal time in that region. For the plasma torus, the only two spacecrafts that have directly measured it are Voyager 1, and Galileo. And those orbits pass through the plasma torus at specific conditions, and we can use them to extrapolate and try and figure out what the rest of the material looks like. Ground-based observations really only look at the dawn side here at 90 degrees orbital phase of Io and the dusk side at 270 degrees. And we can use an effect called parallax to get a little bit of angle away from that. So if we were exactly along the Sun-Jupiter line from Earth on our measurement, we would measure exactly what the conditions at dawn and dusk are. But because Earth is orbiting the Sun, we get a little bit of an angle in one direction or another to measure an offset in local time of this electric field. So through parallax, we can figure out what the direction of this electric field is, and that direction that we're getting is overall perpendicular to the plasmoid effects that Galileo observed. So the equation of V cross B, which is causing the electric fields, does have this perpendicular cross product component where plasmoids are moving away from Jupiter in the pre-dawn sector, and that electric fields is in the post-dawn to post-dusk sector. So it's at exactly a right angle to it. But the magnitude of the electric fields that we're observing with ground-based telescopes is substantially less than was predicted from these spacecrafts. They had thought that it was closer to 6 millivolts per meter, and we're observing about 0.4. The orientation is pretty poorly constrained overall. So long-term measurements are needed in order to understand exactly the direction of this electric field. But this is the first time that we've really understood what the variability of the electric field in Jupiter's inner magnetosphere is. And sometimes that electric field almost shuts off completely, where it's close to a millivolt per meter. And sometimes it's at past 6, 7, 8 millivolts per meter, where there's a lot of reconnection happening in the Jupiter system. There's a lot of plasma convection going through the magnetosphere for extended periods of time. But the field is also changing on very, very short timescales. And those short timescales form a little bit of degeneracy where it's hard to get the average electric field's orientation. So short-term reconnection in the Jovian magnetosphere is something that we need to understand in order to get the long-term effects.